Hello, good morning. I'm Guy Stevenson. I'm a captain with Virgin Atlantic Airways. As you know, Virgin Atlantic Airways run a mix of aircraft, the Airbus 340 and the Boeing 747-400, both top of the market aircraft with glass cockpits. They've all got 4 engines, but today we're going to Miami on the Virgin 005, and it's a Boeing 747-200, which is a real classic aircraft which you all love flying. It's called the classic aircraft because when the 747-400 was introduced, they wanted to differentiate. We called it the 747 Classic. Now we're in flight dispatch at the moment, and this is where we all meet, and so I'd like to introduce you to my crew. There are 3 of us. There's myself, Alan Bonnock, which is here, who's the flight engineer, also our chief flight engineer, and over there, Adrian Thurley, who's been in the company for about a year. He's an ex-Air Force pilot, also, incidentally, a member of the Red Arrows, and also the leader of that August aerobatic team, but no aerobatics today. What we're going to do now is have a look at all the paperwork. There's usually quite a pile of it. It can be described under 3 headings. There's the weather, which is probably the most important thing, then the flight plan, and then the performance data. The weather is this sort of thing. This is a synoptic chart of the Atlantic crossing. There's England, America here, and Florida down here. We've coloured in the area which will probably be cloudy, has been forecast to be cloudy, and our route is this line here. So what we're going to do is leave from Cornwall, go right across the Atlantic to a place which is just to the south of Newfoundland, and then fly down off the coast between 100 and 200 miles direct to Miami. This area here with these black lines are jet streams, and the wind speed there is varying between 85 knots and 110 knots, which is really quite strong. There might be a few bumps there, and it is in fact forecast. It's associated with the frontal system. On the other side, typical for this sort of time of the year, we do get some thunder showers, and the worst bits are the pink bits, and then general cloud, the yellow bits. We also have a list of forecasts, and here they are, lots of them. And the idea is that we look at this piece of paper and study the weather en route and for our destination, and just to make sure that we don't need any extra fuel in case the weather's very bad, which it seldom is. Now, once we've done that, we have a look at the flight plan. We get this from the United States. It's called Phoenix. This is the first page, and on this we get a lot of information about weights of the aircraft. And for example, today we're going to be taking off about 315 tons. That's metric tons. Carrying 115 tons of fuel, we'll burn most of that, about 100 tons of it, so that we'll land about 215 metric tons. What we need to know now from the flight engineer is the condition of the aircraft for our flight today. So perhaps, Alan.
Certainly, I've been in contact with the engineers. The aircraft came in fully serviceable, and obviously it's going to be therefore serviceable when we take it. They put on at the moment 110 tons of fuel, and they're just waiting for our final decision to top it up to whatever we want. And it should be ready for our arrival in about 5 or 10 minutes' time.
All right, so when you get out, perhaps you could tell them we're going to take 115 tons today in view of the weather conditions.
Absolutely, okay.
Adrian Thurley has been working out the performance data. So here we are. Perhaps, Adrian, you could discuss what you've worked out.
Well, the first thing we've got to do is establish the exact takeoff weight of the aeroplane. The zero fuel weight has gone down, as we discussed, just over 2 tons. Guy has decided to take some extra fuel for the possibility of thunderstorms in Florida. So our takeoff weight is going to be, as close as we can work out at the moment, 318.7 tons. With that weight, we then go into our performance book to find out our takeoff speeds and the speeds at which we can abort the takeoff. It also tells us our takeoff power setting, which we'll be using, and today that's quite a bit less than we could use in an emergency. We've got in the order of 40 tons less than we could take on this runway with today's weather conditions. And the assumed temperature that we're working to is 46 degrees. And that's all set to go.
What we've shown you is just a few of the calculations and decisions that we have to make here in flight dispatch. Of course, a lot of other decisions that we do have to make, but most of those will be made on the aircraft, in which case what we're going to do now is to go out to the aircraft and do our preparations there, and if you'd be so kind to join us, we'd be very happy to see you there.
While Guy and Adrian are making their way into the cockpit to get themselves settled there, I'm going to have a look around the outside of the aircraft to make sure there are no obvious signs of damage or problems concerning the engines sucking in foreign objects when we get them started. It takes quite a long time, it's quite a big aeroplane, but if you'd like to follow me around, you'd be very welcome.
Well, here we are on the flight deck. Welcome to it. We've been quite busy, in fact very rushed indeed. We're just about ready to go now. We're just going to do some checks, get our load sheet, get our air traffic control clearance. When we're in the cruise, we'll have a lot more time to be able to speak to you, and so, well, here we go. Briefing. I'm going to do the takeoff. It's a flap 20 takeoff and a standard cleanup at 1,000 feet above the ground. It's 1,200 feet on the pressure altimeter. It's going to be a Sampson 2 mic standard instrument departure, or SID, which is described as ahead via the Golf Yankee, maintaining a track of 262, and left to intercept the 247 Midhurst to Midhurst. And at Midhurst, we turn right onto the Midhurst 262 radio to Southampton. Now, the altitude restrictions are Midhurst 10 above 2,500 feet, Midhurst 8 above 3,000 feet, and Midhurst at 4,000 feet. So 4,000 feet and alt salamed. What I've done is selected Midhurst on the number 1 and 247 in the window. You've got IWW, I think, haven't you? Yes, yeah. Which is 110.9 for the emergency turn, and I've got 265 on both the NDVs. Alan, on this takeoff, could you tell me of any malfunctions? If I decided to abandon the takeoff, our close the throttles, go onto the foot brakes, make sure I lift the speed brakes, and I'll go into reverse idle on all four. Tell me which ones to select, inboards or outboards, and I'll select the reverse as I think fit. If I elect to continue, I'll say go, in which case, when I'm safely airborne with the gear up, could you restate the emergency, Alan, please? I'll call for the drill between the two of you, and I'll take the radio, fly the aeroplane, and when I get to 1,000 feet, I'll go to alt hold, and follow air traffic control instructions. There is an emergency turn. If we have an engine failure before 1.4 DME, we turn left 15 degrees. The transition altitude is 6,000 feet. The sector safe within 25 miles is 2.2, that's 2,200 feet, and within 100 miles is 3,500 feet. Anybody got any questions?
No, understood.
Briefing complete. So let's do the INSs.
No.
INS, present position then. Stand Juliet 32, north 51094 and west 000100.
Check.
Turning points or waypoints. Number 1 is Southampton, right, 50573 and west 1206. 2 is Gibso, north 50451 and west 2303. 3, Land's End 50081 and west 5382. 4, Gapley 50 north and 8 west. 5, Gunso 49042 and west 11447. We've just got a bit of time, so what I'm going to describe to you is what actually happens on takeoff. When we're facing down the runway, and we've finished all our checks, what I'm going to do is stand the throttles up so the engines are stable, and then between myself and the flight engineer Alan, we're going to increase the power to the takeoff power settings. The airspeed will increase. What you'll hear is Adrian saying speed increasing. You'll call 80 knots, and what I do is take my left hand off the tiller, which is this thing here, and put it on the control column. The next call you'll hear is V1, which is the stop-go speed for this particular runway. The next one is rotate. I pull the stick back and rotate the aircraft so that we climb out at about 15 degrees nose up. And then the next call you'll hear is V2, which is our takeoff safety speed. And then we climb out at V2 plus 10, and when we get to 1,000 feet above the ground, we lower the nose and start to accelerate and increase our speed and bring the flap in sequence according to the bug settings that we've got on our airspeed indicators. So we'll accelerate to 250 knots unless they give us clearance to increase our speed to our climb speed, which will be about 320 knots today.
Okay, cockpit preparation procedures.
Complete?
Complete.
Complete. Oxygen mask and quantity.
Checked?
Check.
Checked. Flight control power switches.
On.
Body gear steering.
Armed.
INS mode.
Nav.
Emergency lights.
On.
Cabin signs.
On.
Stall warning.
Normal.
Probe heat.
On.
Window heat.
On.
Radios and clocks.
Set.
Set.
Set. Altimeters.
QNH 1017 set and cross-checked.
Pin 17, set and cross check.
QNH set and cross check. Airspeed and EPA.
Bugs set.
Bug set.
Bug set. Max airspeed warning.
Not fitted on this aircraft.
Start levers.
Cut off.
Fuel.
Is 115 tons and set for starting.
Pressurization.
Auto and set.
Flight data recorder.
On.
Gear pins.
Removed.
Briefing.
Stated.
Before start checklist complete.
Okay, awesome.
Ground Virgin 5, we're now ready to start on 32. We need to start 2 engines before moving and then we'll want to push.
Virgin 5, start is approved, but for pushback contact ground 121 decimally.
Virgin 5.
And start this engine here.
Okay, max motoring number 3.
Okay, fuel in on number 3. Fuel flow. Light
Okay,
up.
fuel flow 350.
N1.
30%. 100%. 595. And start a cutout. Okay, Max EGT 595.
Chilly.
Okay, number 4.
Okay, let's have a go at 4. $30. $40. Let's start a cutout. 580. EGT 580.
Vision 5 requesting push from stand 32.
Version 005 from stand 32. Roger, your push and start a route.
Roger.
Brakes off, please.
Okay, brakes off at 52, 1052.
5-2.
Yep.
You're up here, yes.
Brakes set to park, please.
Roger, brakes now selected to park, thank you. 1, 2, 3.
Brake set apart.
Okay, when you're ready, we'll start 1 and 2.
Are you clear on 1 and 2?
Turning 1.
Okay, starting 1. Yeah. Just finish the checklist then, please.
Okay. Nacelle anti-ice.
Not required, off.
Aileron and rudder trim 0. Stab trim.
Checked and set.
Checked and set. Start levers.
Idle.
Electrical.
We have got lights, but we know about it. Essentially is normal.
Galley power.
On.
Hydraulics.
Auto normal.
Lockout pin. Is removed and acknowledge my side. Ground equipment.
Okay, my side.
Clear my side. After start checklist.
Okay, ask the taxi.
Ground Virgin 5 taxi.
Version 5, taxiway 3 and 5, hold short, taxiway 2, QNH1017. I'll get you to a holding point as soon as I can.
3 and 5 to hold short of 21017 Virgin 5.
First left. Hold short of.
Okay, everybody ready?
Parallel taxiway. All ready.
Yeah.
Brakes
I've
ready.
got to accomplish this alternate procedure.
All right.
Is it okay?
Okay.
Okay.
Okay, it basically says if the generator field off or generator open light remains illuminated, which it does.
Right.
Okay, guy?
Yes.
CSD disconnect procedure accomplished.
Thank you.
CSD disconnect can only be reset on the ground. Confirm engine speed is above minimum ground is at minimum ground idle.
You're right.
Okay. CSD disconnect switch.
Right.
Here we go. Number 2 selected. Generator test. Switch. And it's a clean disconnect.
Thank you. Okay, flight controls, please.
Okay. Ready, Alan?
Yep.
2 up, 1 down. Centre.
005, it'll be holding point Alpha North behind Air Malta now, please.
Virgin 5 to Alpha North behind Air Malta.
Which presume is this guy here.
Yeah, Sam Malta.
Yes. To the right running it. 2 up, 1 down.
Okay, rudders.
Full left.
Left.
Centre.
Neutral. Right.
Full right.
Neutral.
Centre. 2 up. Controls. Check. And we have flat 20.
Okay, let's go through the before takeoff check, Alan, please.
Okay, before takeoff checks. Flight and nav instruments.
Aligned, no flags.
Aligned, no flags.
Aligned, no flags. Grab chairs.
I've got 1 up and 1 down.
That's probably first. 1 up, 1 down.
1 up, 1 down. Flaps, please.
20, 20, green light.
20, 20, green light.
2020, and I've got 8 greens at the back. Flight controls?
Checked.
Check. Check. Stab trim.
Trim set. Switch set light out.
7 degrees, switch set, no lights.
Okay, set. Kelly power is off. APU is stopped.
Virgin 5, holding Alpha North, Tower 12422, bye-bye.
Virgin 5, hold it Alpha North, 12422, bye-bye.
Okay, fuel guy, set for takeoff.
Thank you.
Okay, annunciator lights. Is everybody happy why we've got that CSD all light?
Yes.
Okay.
Yeah, because we lost one.
And any changes to the briefing?
No.
Okay, we're down to line, folks. Brake temperatures are okay.
Okay, brakes going on. Through the line, please.
Okay, stand by.
Virgin 5, after the transat departs, line up.
After the Transat departs, line up, Virgin 5.
Radar.
On,
On, thank you.
Transponder.
set code check.
Inboard
Set
landing
code
lights.
On,
Probe.
on,
Probe heat.
on.
The cylinder is still not required. Awaiting body gear.
Virgin 5, clear takeoff, 13605 knots.
Clear takeoff, Virgin 5.
Okay, before takeoff checks are complete.
Ready, Alan?
Yep.
Okay, here we go then.
Engine stabilized.
So 1.44, please.
ASB building both sides. 80 knots.
High controls.
Your controls. B1. Rotate. B2. Positive climb.
Gear up.
Gear up.
ISO.
IS. Showing just 1 degree of drift now.
Okay, set it down.
Then Virgin 005, passing 1,000 feet, Southampton to Mike.
Virgin 5, good afternoon, climb altitude 5,000 feet, squawk ident, no speed restriction.
Climb to 5,000 feet, squawk ident, no speed, Virgin 5. Climb to 5,000 feet, squawk ident, no speed, Virgin 5.
So flap 10.
5,000, no sell out. Flap 10 was that guy?
Yep.
Flap 10. Flap 10 set.
Flap 5.
Beats good. Flap
Line
5.
bar.
Flat 5 set.
Flat 1, please.
Speed's good. Flat 1.
Virgin 5, climb altitude 6,000 feet, heading 270.
Climb to 6,000 feet, heading 270, Virgin 5.
6,000 sell.
6,000 I'll sell out.
sell out, heading 270. Flaps up, yeah.
After takeoff check, please.
Okay, after takeoff checks are complete, I'm reconfiguring the fuel.
Virgin 5, climb flight level 120.
Climb flight level 120, Virgin 5.
120, outside.
120 surroundings. Southampton on my side, please.
I've set 10:13 now and 2 to go.
Okay, radio. Okay, AO pilot in. Also 150 and airspeed indicator.
Virgin Ops, Virgin 5.
Virgin 5, operation, go ahead.
Okay, Virgin 5, chops, 1052, airborne 1116, and Miami 2005. And everything's okay, thanks.
Okay, that's all, Alan, thanks for call and out of the trip.
Okay, bye. Okay, back with you on 1.
Virgin 5, assuming on navigation, going ground Z.
Virgin 005, direct to land zone, thank you. London, it's the Virgin 005, heavy under 190 from 250, heading 260.
Virgin 005, roger, turn right heading 265.
Roger, heading right 265.
Virgin 5, Shamrock, key clearance.
Shamrock, Virgin 5, go ahead.
Shamrock clears the Virgin 5 to Miami on track Juliet to maintain flight level 350, Mach decimal 84 from 49 north, 15 west.
Virgin 005, clear to Miami by track Juliet, flight level 350, Mach decimal 84 from 49 north, 15 west.
Virgin 5, that's all correct. Come back now to your domestic frequency. Good day.
Virgin 5, thank you very much. Good day.
Okay, we've got track Juliet 350, decimal 84.
Welcome to the cruise. We're up at 35,000 feet now, period of relative calm. You probably noticed how busy we were when we were pushing back, starting our engines, taxiing out, taking off and climbing. And now is a period of relative calm. We've had our lunches, so we're feeling quite relaxed. Now, you probably noticed when we were starting the engines, we had a problem with one of the generators. And I'm going to hand you over to Alan now, so that he can discuss this particular problem that we had with with that generator.
The problem that Guy mentioned was number 2 generator, this one here, which we were unable to connect onto its buzz bar. So what we do when we have any abnormality at all is to refer to a document known as the minimum equipment list. Now we'll have a look at this in a moment, but basically what that book does is specify which items of equipment we can dispatch with that are either partially serviceable or unserviceable. And the thickness of this book, which I have here, is indicative of the redundancy that's built into the aeroplane. In other words, the number of things which can be partly serviceable or unserviceable, but we can still safely dispatch the aeroplane. And one electrical generator is one of these items which, although it's not working, the aircraft can perfectly satisfactorily dispatch with this item US. So having established that by reference to this book, we then refer to the operations manual, which tells us in precise detail how to deal with the abnormality as it was shown to us by the amber generator on light failing to extinguish. So we then refer to this book, the operations manual, and in there it'll spell out exactly what we have to do in order to safely operate the aircraft in accordance with the minimum equipment lift. Reference to the operations manual required us to trip the field, which illuminated that light, confirm the output of the generator was 0, and then to disconnect the CSD, constant speed drive, which is the drive system between the engine and the generator. So we can now go with, in fact, 3/4 of our total capacity. However, having said that, under any sort of normal operating conditions, we are only going to be using the equivalent of 1 generator load anyway, so we've still got 3 times as much capacity as we're ever likely to need.
Now we've got a bit of time, it might be just as well to show you the pilot's instrument panel. These are instruments that any pilot will recognize, and they're arranged in a standard T configuration. Now, I'll point them out to you and go through them one by one. This is the airspeed indicator. It's a combination airspeed indicator and mark meter. We are in fact flying a little slower than normal because we have a restriction at the next turning point, which has been given to us by Gander Air Traffic Control. This is the artificial horizon. We call it the ADI, or attitude direction indicator. And basically it deals with pitch and roll. This is the roll indicator here at the top. The yellow bar, or cross rather, is called the flight director. We can go through that later on. This is the radio altimeter. It only works from 2,500 feet down to 0, and we use it, of course, when we're close to the ground and for when we're coming into the flare mode. This is the altimeter. As you can see, it says we're at 35,100 feet. Down here in the roll mode, this is the compass. Over here is the rate of climb and descent indicator, the VSI. And we'll show you a rate of climb up to 6,000 feet a minute, though we never climb that fast, and vice versa, and a rate of descent. This one here is an odd instrument. It's only on one of our aircraft, but it really describes our true track between the 2 turning points that we're flying between, which are designated on or placed in our flight computers, the inertial navigation system. And over here is another instrument which most people can recognize. It's called an RMI, and is basically just a repeater compass. But it also has it superimposed on it, some non-directional beacons and some VORs, or it's the VHF beacons, navigation beacons really, which we can select by moving the rabbit's ears, which are at the bottom of the instruments, these rabbit's ears here, and you can either select VOR or NDB. Up here, that's a navigation receiver, and over here that's a navigation receiver as well. You can select on here VORs, which are basic navigation devices, or instrument landing system frequencies. This middle panel here is the autopilot and flight director. This particular window here shows 35,000 feet, as I mentioned to you already, and it programs the flight director and the automatic pilot, so that when we arm that, the aircraft will level off at that altitude. This is the heading knob, So if this navigation mode switch is in heading, we can control the aircraft left and right by means of this knob here. We're in inertial navigation mode at the moment, so we're navigating between two waypoints in the inertial navigation system. But if I go to heading, I can turn the aircraft left or right with this knob here. There we are, we're on about 274 degrees at the moment, magnetic. This is the course. The course really is track. It's the American term for track that we're following. It's also a magnetic track. This course here is for the left-hand side of the aircraft, and this course here is on the right-hand side of the aircraft. These paddle switches are the autopilot. It says AP here, autopilot. With this paddle switch in the command position, the aircraft is being flown by the left-hand autopilot. This one has got two autopilots. If Adrian was flying the aircraft, he'd use his inertial navigation system and his navigation devices for flying the aircraft, so he'd use the B automatic pilot. This is the speed mode switch and is used, generally speaking, in the pitch mode. This is VS. So if I want to go down at a certain rate of descent, what I'll do is select VS and control our rate of climb and descent using this wheel here. Once I've established the speed for the descent or the climb, I can switch this mode switch to indicated airspeed, and the aircraft will control the speed that I've selected. Flight director is the yellow cross on the attitude direction indicator. If you have a look at the horizon, you'll see a little orange dot. Basically what happens is you can program that cross, that flight director, using the navigation mode switch and the speed mode switch. If I was flying it manually, what I'd do is fly the orange dot so that it's covered by the cross. The automatic pilot does this by itself. And I think that's basically all I need to tell you about the flight instruments panel, and I can hand you over to Adrian to give you a brief description of the overhead panel, and to Alan so he can give you a description of the engineer's panel.
If we have a look now at the overhead panel, this basically controls a variety of systems which all three of us need access to. If we start at the top left, these are flying control power switches, which in fact are only ever used by the ground crew for ground servicing. We don't touch that in the ground, in the air. The next two switches are control the yaw dampers, and we would only select those off in the event of a failure. The anti-skid system likewise remains on all the time, but we do have the option of disconnecting it. This one we do use on the ground. It's the body gear steering. Because it's such a large, heavy aeroplane, not only does the nose wheel turn, but the main wheels turn in the opposite direction to help it get round sharp corners. So when we go below 20 knots, we arm the body gear steering. Below that we've got the auto brake, which we use for most landings, has various settings, minimum, medium and maximum. And this applies the foot brakes automatically for us, holding a set retardation until such time as we disconnect it, either by touching the brakes or turning this off. Up the top here we have 2 of 4 switches, and these are probably the most important switches in the aeroplane in the event of emergency. They come on to show us that there's a fire in 1, 2, 3 or number 4 engine, along with other warning lights that we get on the front of the aeroplane. And we would pull these in the event of an engine fire, which does a variety of things, including disconnect the electronics, the hydraulics, and of course fire the fire extinguisher for that particular engine. So this is something we play with a lot in the simulator and hopefully never in the aeroplane. Below it we have the engine ignition system. 2 lots again, this side for engines 3 and 4. We have 2 totally separate ignition systems for use in the air, system 1 and 2, and we have at the other side, ground starting, which allows us to feed duct air into the engine to turn it before we feed in the fuel and the ignition to start it. Below that, one of 3 control units for the inertial navigation system. Very straightforward. It simply turns it on to warm it up. We align it to our current position or use it in nav while we're flying from A to B, and we should never have to touch it at any other time. Alternate gear extension here is exactly what it says, an alternate method of lowering all of the wheels if the hydraulics fail. And essentially what it does is disconnect all hydraulic power and the uplocks and allow the wheels to fall under their own weight, which is quite substantial. Below that, one of 2 compass controllers, which only has two settings really. One that it's connected to a magnetic control unit in the wing, or the other one that it's just a straightforward gyro. Then one of the control units for the 2 HF sets that we've got, which is a very long-range radio, our only means of communication across places like the Atlantic or the Pacific. Up here we have 3 more fire indications, one for a fire in the wheel well, one for the APU, which is the auxiliary power unit, the little jet engine at the back. You'll hear more about that with Alan, and one for the lower cargo bay. Apart from the normal ignition system we talked about, we also have a totally separate standby ignition system. Again, ignition 1 and 2, which is our final method of starting the engine should all else fail. Below that, part of the connection to the black box that you've heard so much about, the cockpit voice recorder here with a microphone. Switch for the emergency lights for the main cabin. Doesn't turn them on, it just arms them. This is the selector for the INS, which we talked about earlier. And this is the basically the communication system within the aeroplane. We use this to dial particular stations on the aeroplane. Basically one for the left and 2 for the right. From here we can talk to any one of the phones at the passenger doors or upstairs here in the lounge, and likewise they can talk to us. We can also use this to select the PA to talk to all the passengers, and we can also use it to talk to the ground crew when they're connected to the aeroplane in the nose wheel bay. Below that, the switches, which are fairly self-explanatory. No smoking, which of course is now on all the time on Virgin flights. Fasten seatbelt fine. Ground crew call, or if we want to get hold of the ground crew, plugged in underneath. And the flight deck door release. Below that are 2 windshield wiper switches, one either side, and indeed we have windscreen washers as well, although we very rarely have to use those. Going back up here, the other 2 fire switches we've talked about, the ignition system to match that one, and the INS selector. Then we come down to another alternate system, this time for the trailing edge flaps, and below them for the leading edge slats. So again, in the event of a hydraulic failure, we can use these switches to use electrical systems to ensure that we can always get the flaps out for landing. Second HF selector box here, and the compass selector to match the other 2. Up to this side, a series of test switches here. This one tests a system that tells us if we overspeed the aeroplane. I won't do it now, or I'll make Guy jump out of his seat. This one is over rotation, which is another system which, should we rotate the aeroplane too swiftly on takeoff, which if we really overdid it, we could strike the tail. Stall warning, 2 totally separate systems, which make the stick shake and push forward if we get the aeroplane too slow and approach the stall. The cell anti-ice, which is something we use quite a lot. Whenever we go through moisture, which means cloud or rain or snow, below a certain temperature, then we select anti-icing on the engines. This is just hot bleed air which is fed back into the front of the engine to prevent ice forming. Wing anti-ice, on the other hand, we hardly ever have to use. This is hot air fed onto the leading edge of the wing, and this removes any ice that might have built up. But in my limited 1 year on the airplane, I've never seen it used yet. The probe heaters are the probes that stick out of the airplane, which are used to sense the aerodynamic pressure and give us all our height, airspeed and Mach speed. They're always on for flight. The window heat, likewise, we have filaments in all of the windows around the front. These are put on the ground and stay on throughout flight, and are designed to stop the windows, basically, obviously freezing up or frosting, and equally importantly, to stop them cracking and getting brittle in the outside air temperature, which is minus 58 degrees at the moment. The final part of the overhead panel is this long strip here, and this basically controls all the external lights for the airplane, and there are quite a large number. Moving down from the overhead panel to the center panel, where we keep our left hand for all approaches and departures. First of all, coming forward, this is the landing gear selector switch, which is up, down and curiously perhaps off. Off is in fact the selection where there is no hydraulic pressure at all to the system. So once the wheels are up and locked up, we select this to off, so we can't have any leaks from the system. Moving back, I'll leave all the engine instruments for Alan to talk about. Over here on this side we have the speed brakes, which are basically spoilers that come out of the wing to slow us down if we get too fast, and also to kill the lift on landing. Next we've got the stab trim. This is the manual stabilizer trim. We would normally use the electronic switches on the control column, but these are there to override if necessary. Next, the parking brake, which obviously we only use on the ground. And then a selector here, which we put into the appropriate section depending on the center of gravity of the airplane at takeoff, which can vary enormously. We basically tell it what the center of gravity is, and this makes sure that we've got the trim set correctly. Next we have the 4 thrust levers, numbered, as are all the instruments and all other things relating to the engines, left to right, 1, 2, 3, 4. Forward, obviously for more power, and back to flight idle. Also at the front of this, which you can't see probably from there, are 4 more levers which we would pull upwards and then all the way back to select reverse thrust on landing. We can't select those in the air, not that we would ever want to. Below them, these 4 switches, which look fairly insignificant, but actually control all the fuel into the engines. These are selected on in the start sequence, and they stay there until we come to shut down at the far end, unless of course we had something like a fire, in which case we could use those to cut off the fuel, or the fire switches up here. Moving over, the flap selector lever is here, currently in its up position, comes all the way to 30 degrees of flap, and the 2 gauges up here show the corresponding flap positions. Moving down to the final part of the center console, these are all, or almost all, radio selectors. This is one of 3 VHFs that we have. This is the one we traditionally use for talking to air traffic, the one we're talking to them on at the moment. And we have 1 more here, and 1 more here. These 2 we use for ADF, automatic direction finding. Pretty old pieces of kit now, but still in use around a lot of airfields for the final approach fix. Here we have the 2 wheels which Guy talked about earlier, which we can use to control the airplane when it's being flown by the autopilot. This is one of the 3 inertial navigation systems, which Guy will describe in more detail later on. Finally, here we have the radar controller for our weather radar. We have 2 radars, selector switch here between the 2, and two screens either side in the front, which you can't see from there, which we use obviously to try and make sure that we avoid, in particular, cumulonimbus cloud, in other words, thunderstorms. Just simply a standby or normal selector on there, and a pitch for the radar here, such that we can select it, whether we're climbing, descending, or in level flight.
The flight engineers panel, and as can be seen, it gives us indication and control of practically all of the systems on the aeroplane. So what we'll do, we'll work our way around the panel, looking at each of the bits and pieces in turn, and describing what the panel controls and what indications we get from the system. And starting right at the top here, we have our APU panel. APU, Auxiliary Power Unit, and that's a little engine in the tail of the aircraft, which we can start up when we're on the ground. These generators are able to power up the whole electrical system of the aircraft, so we're completely independent of any ground electrics. Similarly, the APU has got connected to it what is called a load compressor, and that produces a large volume of air supply, which we can use for air conditioning the aircraft. We'll be coming onto the air conditioning panel later, and we can also use that air to run our air-driven hydraulic pumps, which enables us therefore to be completely independent of any ground sources, in that we can supply ourselves with electrics, air and hydraulics from our own APU, which is in the tail of the aircraft, as I said. And this is particularly useful when we go through some of the more remote airfields where these ground facilities may not be available. It's a great benefit we have on this aircraft. Continuing down the panel, we then move on to the electrical control panel. A little bit we saw earlier on when we were talking about the generator abnormality. Basically, we have got 4 generators, one on each engine, each generator capable of delivering 51 kilowatts. Now you can see at the moment, looking at the load, number 1, number 2 of course is dead, number 3 and number 4, the actual total load across the aeroplane is rather less than 10, 12, 27, 37, is less than 50 kilowatts. So we can see that with the load that we've got on the aircraft at the moment, it is still easily supplied by one generator on its own, and we've got 3 supplying it. So we can see the redundancy that's available. As we've already demonstrated, the loss of a single generator doesn't really represent any sort of problem at all. The field switches, which enabled us to disconnect or rather to shut down the generator, although it's still rotating. Then the CSD switches, which enabled us to disconnect the CSD from the engine, and the CSD oil temperature indicators. And it's interesting to see that this one, the one that we disconnected, the oil temperature is much higher than the ones which are working. And the reason for that is that because we have disconnected it, remember we did that before we took off, there's no circulation of oil through the oil cooler, and therefore the oil isn't getting cool. And it's just sitting there absorbing heat from the engine, causing the temperature to go up. An additional job that the ground crew are going to have to do when we arrive at Miami is to change that oil, because obviously it's being contaminated by sitting there for about 6 hours at a very high temperature. Moving across to this little panel here, it consists of a frequency meter, a voltmeter, and a series of selector buttons. And this enables me to have a look at the output of each of the generators. At the moment we've got number 3 generator dialed up, where, because it's all serviceable, we've got 115 volts and 400 cycles. If I select number 4, we'll expect exactly the same sort of indication. 400 cycles, 115 volts. Remember, number 2 generator is shut down, so when I select number 2 generator, predictably there's no frequency and no voltage because the generator isn't in fact turning. Go on to number 1 and everything is back to normal as it should be. I can also check on these meters, if I want to, the output of any ground generators, which clearly we haven't got, the APU generators, which we haven't got going because we've got the APU stopped. Above this, a selector giving me control of the power source for essential AC. It normally comes from number 4 AC bus, but I have the option, should I choose to do so, of deriving it from numbers 1, 2 or 3 generators. This switch gives me control of where the standby power is being supplied from. And finally, moving up here, the DC ammeter and DC voltmeter, which very much like the AC ones, is telling me whatever I have got selected here. And I've actually got at the moment the aircraft battery, which is 28 volts, and there's no load on it, quite predictably. If I have a look at the TRUs, the transformer rectifier units, I'd expect to see 28 volts and a plus to a greater or lesser extent, giving indication of the load on those bus bars. And that just about completes the very quick description of the AC and DC electrical panels on the aircraft. Moving on now to the supplementary engine panel. The top indicators are the N2 indicators, the RPM, that is, of the core part of the engine. The N1 indicators, as they're called, which is the fan, are on the front panel. Continuing down, the oil pressure indicators, exactly the same as the ones you might find in your car, as indeed are the oil temperature indicators. Oil quantity, letting us know how much we've got in the oil tanks. And finally at the bottom, the breather temperature indicators, which give us an indication of the state of the internal seals on the engine. If they start deteriorating, then these temperatures will start increasing and we'll take the appropriate action. And that completes the supplementary engine panel. The fuel panel, one of the largest pieces of the whole flight engineer's panel, and perhaps one of the most important as well. It's difficult to assess actually anything that's more important than something else. The fuel system consists fundamentally of 1, 2, 3, 4, 5, 6, 7 tanks, with 6 of them, 3 each side, in the wings, and in the centre fuselage, a large fuel tank. The total amount of fuel that we can carry is approaching 160 tons, but we don't need that on very many occasions. Indeed, today we only require 115 tons. Where we require less than the full load, we tend to put the minimum possible in the centre tank and fill the wings. And the purpose of doing that is to relieve what is called the stress loading on the aircraft. The fuel is delivered from the tanks to the engines by means of booster pumps, all of which are on at the moment. And the tank from which we are taking fuel is controlled by a combination of switching the pumps either on or off and opening or shutting the cross-feed valves. At the moment, we're in tank-to-engine configuration, where this tank, number 1 tank, is feeding number 1 engine, number 2 tank is feeding number 2 engine, and similarly, number 3 tank, number 3 engine, and number 4 tank to number 4 engine. These tanks here, known as the reserve tanks, are at the moment still full of fuel, and we keep them full of fuel until sometime on the approach. Again, the idea is to keep as much fuel outboard of the wings for as long as possible to once again spread the load of the fuel throughout the whole wing. When we get on the approach, or indeed actually in the descent, I'll open this valve here and this valve here, and the fuel will drain down into the 1s and 4s, and we should find then, if I've done my sums properly, that the contents of this plus this will equal that. Moving up the panel, we come to the fuel heat switches, which at the moment are selected to auto. Now the reason for requiring these is that the fuel in the fuel tanks gets extremely cold. Indeed, I can monitor the temperature of the fuel in the tanks by selecting number 1 tank, and we can see that the temperature is minus 22 degrees centigrade. Now the problem with this is that any water that's in the fuel, and there's always some degree of water in suspension in the fuel, is likely to turn to ice. And the problem with fuel at that temperature, developing ice crystals, is that the ice might start blocking the fuel filters. So what we've got to do is to heat the fuel to prevent this ice crystallization forming. We can see at the moment I've got number 1 fuel tank selected, and we can see that the temperature is minus 22 degrees centigrade. Now by the time the fuel gets to the engine, it is going to be slightly warmer, so I can select that. But we can see that it's still minus 10 degrees centigrade, and obviously any water that's in suspension would start turning to ice at that sort of temperature. If it does turn to ice, then we stand the risk of blocking the filter. So what we need to do is heat up this fuel to melt any ice that might have started accumulated in the fuel filter. And we can do that by selecting the fuel heater to on. That puts hot air through the fuel, heats the fuel, which then heats the filter, melts the ice, and protects us against any blockage of the filter. If we compare this now to number 1 engine is 50, number 4 is 50, they've both got the heaters on, whereas number 3 engine, which hasn't got the heater on, we see the temperature of the fuel is minus 5. The final bit of the fuel control panel are the fuel used indicators, 1 for each engine, number 1, number 2, number 3, and number 4. And you can see that we've used just about 20 tonnes of fuel per engine. That's a total of 80 tonnes. It seems an awful lot of fuel to have burnt, but it's got to be remembered that we've carried 45 tonnes payload. That is 290 passengers, plus their bags, plus freight, at a speed of over 550 miles an hour. So if you compare load times speed times fuel burnt, it's still an economical way of moving something from A to B. Moving on to the pressurization and subsequently the air conditioning panel. Looking first of all at the pressurization, at the moment we've got a cabin altitude of 6,700 feet. The aircraft at the moment is at 39,000 feet. The effect of this is that our differential, that is the difference between the pressure inside the cabin and the ambient pressure outside, is 8.4 pounds per square inch, which is actually quite high. The fact that the cabin is at 6,700 feet enables us to reduce the cabin differential. If, for example, we maintain sea level pressure in the cabin, it would maybe be slightly more comfortable for everybody, but it would require the aircraft to be so strong that in fact it would never be able to get up that height anyway, so it'd be a waste of time. So all aircraft do this. They allow the cabin to climb, but not to the same extent or to the same rate as the aircraft is climbing. 6,500 feet, as I say, is only slightly higher than Nairobi or Johannesburg. But one of the effects of this altitude is that, from a passenger's point of view, it accelerates the effect of alcohol, the doctors tell us. With every scotch that you have in the air, it's equivalent to having 3 scotches on the ground. This may seem like a good idea at the time, but it doesn't half accelerate the jet lag, which is often not jet lag at all, it's simply a hideous hangover. The air conditioning panel, it consists of 3 totally independent, again, air conditioning packs being supplied from the pneumatic manifold, which consists of a pneumatic tapping off of each engine. Once again, this demonstrates the redundancy that's built into the systems. We have 4 pneumatic bleeds, 1 from each engine, as I've said. We could actually perfectly adequately cope with 2 of them being inoperative. Similarly, we have 3 air conditioning packs. The air conditioning on the aircraft would work perfectly well with only 1 of the 3 working. So we've got heaps of redundancy or spare capacity built into the system, which is one of the big attractions of this aeroplane. That air delivered from the air conditioning packs is controlled, the temperature of it is controlled, and we are able to select the appropriate temperature for each of the compartments. Again, this is a big advantage of this aeroplane in that to a very large extent each compartment or zone in the aeroplane is able to be individually controlled. One often finds on smaller airplanes that one part of the fuselage or the cabin is extremely cold while the other one is extremely hot. That is not the case on this. We can have all of the compartments at exactly the temperature that is required by the passengers. Big advantage. Then moving across to the next panel, the cargo fire protection panel. This consists of a series of detectors which will tell us whether or not the cargo compartment detectors have recognised smoke. If they have, what we will do is to fire both fire extinguishers, which will extinguish any fire that might be burning in there. The nacelle temperature indicators, the engines in other words, are all perfectly normal and in the green at the moment. Should any problem arise, then the indicators will increase through the amber into the red. And as Adrian explained to you earlier, it will illuminate the fire warning light and will stop the engine. One of the big advantages of these is that we've got what is called a double loop system. So it requires both loops or both detector systems to confirm that we've got a problem. The effect of this double loop system considerably improves the reliability of the overheat detector system. Then moving up here, the cargo heat. This enables us to put some heat into the cargo compartments. This is particularly useful in terms of people's baggage. Should the cargo heat not be working, you will find it out when you go to change into your underwear at the hotel. It'll be very cold and crisp. Down the panel, wing overheat detectors will tell us if one of our pneumatic ducts that we talked about earlier has split, allowing hot air to escape into the wing. Again, should this happen, there are procedures to cater for this. From the wing overheat panel down to the hydraulic panel, and you can see from this a fairly large panel, and it consists of indication and control of our 4 hydraulic systems. Hydraulic contents indicators for each of the 4 hydraulic systems, control switches for the pumps, of which we have 2 per system. We have the engine-driven pump and additionally an air-driven pump. So should an engine fail, obviously the engine-driven pump will stop, but we'll still be able to maintain hydraulic pressure by means of the air-driven pump. Either or both of the pumps delivering into the system, and we've got indication of the system pressure on the top indicators. Hydraulics, a vital part of the aircraft systems. in that the flying controls are all powered by hydraulics, but a very clever permutation of hydraulic systems means that any single one hydraulic system will provide power to all three primary flying controls, that is the aileron, elevator and rudder. They also supply power to the landing gear and the flaps. But again, as Adrian has already shown, we can still get the undercarriage down and the flaps down by means of alternate system should the hydraulics fail. So once again, a demonstration of the reliability and the redundancy built into the systems. The airplane is still perfectly flyable on 1 out of 4 systems. We could lose 3/4 and still not have a really serious problem. And that just about completes the main components of the flight engineers panel on this aircraft.
Virgin 5 Heavy, calling left heading 170.
Left 170, Virgin 5 Heavy.
Gear down, flap 20.
Gear down. Flap 20.
Virgin 005 Heavy, Mom, you with me? Virgin 5 Heavy, we're with you. Virgin 5 Heavy, did you want 9 left today? Virgin 5 Heavy, 8, sir, if we can go now. Virgin 5 Heavy, change to 9 left, clear to land, wind 140 at 16. Change to 5 left, clear to land, Virgin 5 Heavy.
Okay. Flap 25, please.
Speed's good, flat 25. 110 straight.
Yeah.
Knot headwind component, 5 left. It's fluctuating between 15 and 20 on the nose.
Okay.
Still 5 left.
Let's keep an eye on that. In case
No
we get
wind shear at the moment.
a wind shear.
Hundred's a decision.
It's carrying a bit of extra speed because of that, I might add.
Okay, wind shear indicator.
Okay.
3 left. 22 knots.
Decide.
Lands.
20 knots. $50 feet. And 30 feet.
Virgin 005 Heavy, ground point 8. Ground point 8, Virgin 5 Heavy. Ground Virgin 5 Heavy with you. Virgin 5 Heavy, land the ground, taxi to the ramp, what you gate? Bravo 11, Virgin 5. Okay.
Okay, 1, 2, and 3.
Brakes set to park.
Okay, to chop the engines.
Okay, number 1, 2, number 3, number 4, all running down nicely. Welcome to Miami. We've arrived now after 9 hours and 13 minutes. We're looking forward to 24 hours rest. We're going to the hotel in a moment for a nice cup of tea or something different. Well, actually that's not strictly true. It's 24 hours later. I'm wearing a different shirt. It's a short sleeve shirt. It's very warm here in Miami, and we're sitting on the flight deck, the same stand, and we're just about to go back to Gatwick. It's going to take 7 hours and 43 minutes. The difference in the flying time, of course, is because we have tailwinds going in an easterly direction. And we're just about to start the engines. We'll be airborne soon, and when we're in the cruise, we'll be able to discuss with you one or two of the things that we didn't discuss with you on the way out. So we'll be talking to you later. Miami ground, it's the Virgin 006 on Bravo 11, request pushback.
Red 006, pushback, labs ready, taxi.
Okay, thanks.
Virgin 006 Heavy, fly heading 090, runway 90 left, clear for takeoff.
Roger, Virgin 006, 090, clear for takeoff.
Your first meters. Okay, engine stable.
Airspeed building, both sides. 80 knots. Your controls. V2. Positive climb.
Gear up, please.
Gear up.
ISO.
IAS hold.
Virgin 006 Heavy, heading 090, contact departure. Have a good flight.
Roger, departure 11945. Bye-bye. Miami departure, good evening. It's the Virgin 6 Heavy, passing 700 feet.
Virgin 6 Heavy, good evening, radar contact. Flying 080, join the valley transition, climb maintain 7,000.
Climb to 7,000, 080, join the valley transition.
Lap 5.
Speed checks, lap 5.
Lap 1, sir.
That one set.
Virgin
Yes,
6 Heavy, climb maintain 16,000.
Virgin 6 Heavy to 16,000.
Changing fuel configuration, guys. All cross speeds open.
Radio.
Virgin 006, when able, flight heading 030, join landing group 7, westward of change.
Roger, 1 able, join Atlantic route 7030. That'll be in about 30 miles.
IS.
We're in the cruise now, about 100 miles off the American coast. We're at 33,000 feet. We're in cloud, and there still is a bit of sun. In about an hour's time, it'll become night. Adrian, my first officer, is flying the aircraft at the moment, so I'm able to talk to you. Now, what I'm going to do is show you some of the engine instruments in the front panel. This top row is the engine pressure ratio. The engine pressure ratio is a direct indication of engine power. It's the ratio of the pressure at the front of the engine to the pressure at the back of the engine, and therefore a direct indication of engine power. At the moment, it's showing 1.47. It's quite a lot of power, and the reason is, of course, is that we're quite a high level and quite a heavy aircraft. The next row of gauges is N1. That's a percentage indication of the rotation speed of the big fan at the front of the engine, which we can all see. As you can see, it's about 93–95% across the all 4 engines. The next row, exhaust gas temperature. The exhaust gas temperatures are quite high. The reason is, of course, we've got quite a lot of power on, and the aircraft is quite heavy, and for this level the temperature is quite high because we're quite a long way south. The next row of instruments, right at the very bottom, is the engine fuel flow. There are 4 of them, and it shows kilograms per hour. At the moment, and I'll point to the gauge here, this bottom row, each engine is using about 3,500 kilograms. So if you multiply that across the ship, all 4 engines, we're using about 13,000 kilograms per hour. Of course, as the aircraft gets lighter, we'll throttle back to keep the speed under control, and the fuel flow will fall at the other end of the Atlantic to about 2,500 kilograms per hour per engine. We've got one more gauge to look at as far as the engines are concerned, and it is this gauge here. It says EPRL, which is engine pressure ratio limit, and it's a little computer that tells us the maximum power we can use, or the maximum engine pressure ratio we can use in certain modes of flight. As you can see, it says CON. That means continuous. Now what I'm going to do is press the switches on the computer control, and you'll notice that the words change, and so do the engine pressure ratio limits. So continuous is a 1.61. That's the maximum continuous engine pressure ratio limit that we can have in these conditions at this altitude and at this temperature. Now what I'm going to do is press the next switch down here, and you'll see the figures change. There we are, cruise. That's the maximum power for the cruise mode, 1.52. For if we want to climb, which we wouldn't do at the moment because we're too heavy, but later on we will be. There we are. Climb is 1.5859. That's the maximum amount of power we'd use for our climb. And there's one more, and that's go round or overshoot. That's the power that we'd use. We'd have that mode selected, in fact, on the approach, and that's the power we'd use if we had to overshoot because the runway was blocked or something like that, or the weather was too bad. There are one or two more gauges and indications that I ought to show you on the forward panel. There are two flap gauges down here with indications 1, 5, 10, 20, 25 and 30. These are the various angles of flap that we can select. Obviously when we're in the cruise we don't have any flap at all, but as we come into land we change the shape of the wing by increasing the area of the wing by putting our flaps out, and those are the indications of the amount of flap that we can use. 30 is the maximum, and we'd normally land with 30 degrees of flap. There are two gauges. One is for the outboard flaps and one is for the inboard flaps. Beneath that there's another gauge. It's TAS, true airspeed, and at the moment it's showing about 513 knots, nautical miles per hour. This would be our speed over the ground if there was no wind at all. In fact, we do have a tailwind at the moment of about 34 knots, and this is giving us a ground speed down here of 550 knots, so that's probably about 650 miles an hour in our terms on the ground. We use nautical miles per hour. There are other indications as well, a little annunciator panel. And what I'm going to do is press the test switch so you can have a look at it. And these lights come on if small problems occur. It attracts our attention, and then we can go into the appropriate drill if we have to. And really that just about concludes the forward instrument panel for all the gauges and annunciations. It's 8 o'clock in the evening here, just off the American seaboard. And as you can see, the sun is starting to go down. We've got about 400 passengers on board at the moment. They're enjoying their dinner, and in about an hour's time they'll be settling down either to sleep or to watch their videos and to relax. On the other side of the Atlantic, we'll be able to discuss one or two other items that we haven't had time to discuss so far. The sun will be coming up at about 4:30 British time, and the time at the moment in England is 12 minutes past 1 in the morning. Well, as you've noticed, the sun's now up. We're on the eastern side of the Atlantic, about 15 degrees west, which is not far from the Irish coast. The passengers will be waking up shortly, and they'll be having their breakfast. Now, what I'm going to explain to you now is how another piece of equipment works. It's called TCAS, which is Traffic Collision Avoidance System. It consists of a computer and a Mode S transponder, which can best be described as a sort of data link between aircraft which have the same equipment on board. Now what the computer does is create two zones around the aircraft, an outer zone or caution zone and an inner zone or danger zone. Now if an aircraft flies towards me and into that outer zone, the caution zone, what it does is the computer produces an electronic voice, and it says traffic. It's in a sort of American accent. It also produces on the TCAS instrument a solid yellow circle. So we look at the instrument, see where the little blob is, and then orientate our gaze outside the aircraft, if we're not in cloud that is, to see where the other aircraft is. Now if that aircraft comes on and comes into the inner zone, into the danger zone, three things happen. An electronic voice tells me what to do. It says climb, climb, or descend, descend. In fact, there are quite a lot of commands, but those are the simple ones. It also produces on the instrument a solid red square. And probably more importantly, it produces two coloured bands on the rim of the instrument. One is red and one is green. Now, what I should explain is this TCAS instrument, or symbology, is superimposed on the VSI. So when the electronic voice gives me commands climb or descend, all I have to do is raise the nose or lower the nose of the aircraft so that the vertical speed needle goes out of the red and into the green, and by this means we avoid a collision. It's a very clever piece of equipment, and the pilots like it very much. We have another very nice piece of equipment on the aircraft. It's been on aircraft for a very long time, and it's to avoid us having to listen to the high-frequency radio in case somebody calls us. High frequency is very, very long range, but it also picks up an awful lot of static, and it can be very noisy indeed. So what we have on board is a device called cell call, which stands for selective calling. Each aircraft has its own individual code, and this one, in fact, is Bravo Juliet Alpha Hotel, Bravo Juliet Alpha Hotel. The people on the ground know this, so if they want to call us, they dial up that code, and we get a sound from the cell call instrument or controlling device. It just goes ding-dong, rather like Avon calling, and it's just down here. Any moment now, Shanwick are going to cell call us. And now I've cancelled it. So I now know that Shanwick, which is the controlling authority on this side of the Atlantic, is calling us. So instead of having to listen to the HF all the time, I just select the frequency and speak to Shanwick, and by that means we avoid a lot of noise. Behind my head you can probably see a map in the window. This is unusual. The first officer's keeping a good lookout. The idea is, of course, is that the sun's right behind that map, and it's just to keep it from shining right into the camera lens. Anyway, what I'm going to do now is describe the INS, or Inertial Navigation System. We have three on the aircraft. All those years ago when the men went to the moon, they just had one. We have three. Now, it consists of various devices, quite a complicated piece of equipment. Has a stabilized platform, stabilized with gyros, has three accelerometers, for want of a better description, a clock, and a computer. Now, what happens is that how we use this, before the aircraft is moved, when we're on stand, we load into the computer the present position of the aircraft, quite accurately in latitude and longitude. The gyros are spinning up, and we eventually put the inertial navigation unit into navigation mode. I also load into the computer various waypoints, or turning points really, but we call them waypoints, so that as soon as the aircraft starts to move, the accelerometers sense an accelerating force. Now, the interval detector, or clock, integrates that accelerating force, and the result, of course, is speed. Now, what I've done is draw a diagram to show you how the computer navigates. Here it is. Here's our present position. That's loaded in latitude and longitude. The accelerating force is integrated with the time, as I said, producing velocity. The aircraft knows in which direction it is pointed, heading. It also knows where it is on the Earth's surface, or above the Earth's surface when it's flying, of course. And there it is, track. So the difference between heading and track, of course, is drift angle. If there was no wind, the track and the heading would be the same. But as there's some wind today, that's where we would be in still air, in other words, with no wind. That's where we've ended up, along this track. The difference is wind, and that's the vector triangle. Now the computer does this calculation all the time. What I'm going to do is show you the instrument, the number 3 INS, which generally speaking the engineer uses. It's nearest to him, and I'll show you the various functions on the instrument itself. This is the number 3 inertial navigation unit, or the top end of it. Of course the computers are underneath the floor. This is the rotary switch, and I've selected at the moment a heading and drift angle. There's a heading. It's 088.1 degree. That's a true heading, incidentally, not a magnetic one. And that one shows that the aircraft is drifting 5 right. So our track, if I add a 5 to that, it's 093. If I turn this switch to track and ground speed, there you are, 093 is the track, and the ground speed is 533 knots. If I turn the rotary switch to pause, that's position, you can see the latitude and the longitude changing. It's continually being computed. At the moment we're just under 52 degrees north and just to the west of 14 degrees west, 14,238, 237, 235 degrees west, which is quite close to the coast of Ireland. Now, this device here says 3, 4. Those are waypoints 3 and 4. If I turn back to waypoint 4, that's flashing because we're going to waypoint 4. We've put in the computer 51, 20 north and 5 degrees west. Going back to distance and time, at the present ground speed, it's 347 miles, and it's going to take us 38.9 minutes, or 38.8. We're going quite fast. As I mentioned, we're doing 530 odd, nearly 540 knots, nautical miles per hour. That's 9 miles every minute. If you remember the diagram, I showed you that the computer does compute a wind. If I move the rotary switch to wind, there we are. It's 319 degrees true, 320 degrees true. That's 62 knots. And if I press that button, the whole button, it says S39. That means that we've got a stern wind of 39 knots. So although our true airspeed is 488 knots, with plus 38 brings our ground speed up to 536, or thereabouts. What I am going to do now is to show you how we insert waypoints or turning points. We're going to waypoint 4, as I showed you earlier on. Now on the flight plan, Merley is waypoint 4. It's north 5120 and west 5 degrees. It's ringed. I know that particular turning point or waypoint is in the computer. Now what I'm going to do is put waypoint 5 in the computer. It's called Exmoor. What I've done is put this rotary switch onto waypoint and this thumb wheel switch onto waypoint 5. I'm going to press remote, and remote on the other INSs. And by that means, if I load this particular computer, it loads all the others as well. You can see waypoint 5 was 50 degrees north and 50 west. That's just almost by Gander and Newfoundland. But here we go then. So I press this switch here which says north, and the insert light comes on, and the waypoint of Exmoor is 51107. 51107. I check it, it's right, and I insert it. Then I press west, and the west position is 3215. Here we are, 3215. I check it, it's correct, so I insert it. Now, to make sure that I've got that waypoint in correctly, I go to distance and time, I press waypoint change, the light comes on, and I press 4 to 5, or 4 to 5, and the distance between those 2 points is 62. So if I look at my flight plan, between 4 and 5, the distance is 62 miles. So I now know that I put that waypoint in correctly. And what's more, the first officer and the engineer officer, Adrian and Alan, will do exactly the same check, so make sure that not only have I checked it, but they've all checked it as well. So now I know that position Exmoor is correct, I can ring that, and I know it's in the computer. The computer is now programmed for our route as far as Exmoor, and Adrian, my first officer, is at this very moment programming the last few turning points or waypoints to Gatwick. The North Atlantic Track System, NATS, we call it the NAT Track System. Every day across the Atlantic there's a route structure which is constructed by the air traffic control authorities both on this side of the Atlantic at Prestwick and on the other side of the Atlantic by Gander. This is in Newfoundland. Now these tracks are based on the requests of the various airline companies to these air traffic control authorities. What happens is that all the requests are gathered together and the best track system is designed by the air traffic control people. They're separated by 1 degree of latitude and they go across at even numbers, say 50 north, 51 north, 52 north, etc., etc. Now what I've got is a list of these and also a diagram, so I'll show them to you. Here's the list of the North Atlantic easterly tracks. This was supplied by our company, but it really came from Gander. Today we flight planned for track Zulu, and we actually got it. And here's track Zulu. It starts at YQX, which is Gander, and then goes 50 degrees north, 50 west, 51 degrees north, 40 west, and then each 10 degrees of longitude at 52 degrees north. It also shows the flight levels which we're allowed to have on that particular track, starting from 33,000 feet to 39,000 feet. We flight planned for 370, which is 37,000 feet, and we actually got it, so we were lucky today. This is the diagram which shows you roughly the North Atlantic with Ireland and England here and North Canada and North America here. That's track Zulu with 1, 2, 3, 4, 5, about 6 or 7 tracks to the north of us, all separated by 60 miles, which is in fact 1 degree of latitude. Now separation across the Atlantic. Obviously aircraft at the same altitude or same flight level, if they're on adjacent tracks, will be 60 miles apart. If they're on the same track and at the same level, they have to be separated by 10 minutes. And if we're on the same track but close to each other, we have to be separated vertically by 2,000 feet. So you see, it's well organized by air traffic control to keep us aircraft apart from each other. Safety, of course, is the name of the game. I've got one more chart to show you, and here it is. This is called a progress chart. What we do is put on this progress chart our route in latitude and longitude. As you can see, these vertical lines are longitude, and the circle or slightly circle lines are latitude. I put each turning point on this progress chart and connected these turning points, and this is the line or track Zulu that we followed, going this way, of course. There is England, Ireland, and Newfoundland in Canada. About 8 minutes after each turning point, I look at the computer, the present position of the computer, and I make a note of it on here. I now plot that position on the track that I've also plotted on this chart. The track and the cross should coincide. This line in the middle has an arrow pointing that way to Shannon, SNN, and that way to YQX, which is Gander. This is the equal time point. and it is just put on this progress chart to give us an indication of which is the closest station or airport if we had for any reason to return or go on. So once we get there, it's an equal time between Shannon onwards and Gander for our return.
Virgin 006, descend altitude 2,000 feet, report established, climb the runway 26 left.
Roger, down to 2,000 feet and call established on Virgin 006.
No drift, 6 knots.
.100 above decision altitude.
Check.
Decision altitude.
Land. 100 feet. 50 feet. And 30 feet.
Knots.
65%.
70 knots.
65% auto brake line.
60 ground, 50 ground, 40, 30.
Virgin 6, make a
25.
fast right and contact ground 121.8 when vacated.
121.8. Here we are, safely back at Gatwick after some 48 hours. We're back exactly where we started. I'd obviously like to thank Adrian and Alan, my crew. Virgin Atlantic Airways, as you know, has Airbus 340s and Boeing 747-400s, but today you've been watching the Boeing 747 Classic in operation. I do hope you learned something about our operation and enjoyed watching it. Thank you and goodbye.